Welcome to the introductory lecture on structural equation modeling. In this lecture, we'll be discussing the general terms and concepts of structural equation modeling, as well as its overall use. What is structural equation modeling? Structural equation modeling, or otherwise known as SEM, is a general statistical modeling technique that's used to establish relationships among variables. We consider structural equation modeling to be a confirmatory technique in that it tests models that are conceptually derived beforehand. We use structural modeling to test if a theory fits the data. So structural equation modeling is considered to be theory-driven as opposed to data or empirically driven. Essentially, structural equation modeling is a combination of factor analysis and a series of multiple regressions. Structural equation modeling allows us to simultaneously test both the measurement model and the structural relationships that are specified in our model. Structural equation modeling can also be called a variety of other terms. You may hear the terms path analysis, path modeling, causal modeling, analysis of covariance structures, and latent variable analysis. The programs that are commonly used to conduct structural equation modeling analyses are AMOS, LISREL, and M+. Now, for a more detailed description of these various programs, you can refer to Klein's 2005 textbook entitled Principles and Practice of Structural Equation Modeling. Now, before using structural equation modeling, you must of course screen your data to check for any outliers, missing data, as well as to ensure that your assumptions of normality, independence, and linearity are met. Just as a side note, you can still run structural equation modeling using missing data. However, there are some functions that you will not be able to do. One of those being what we'll later on talk about, what we call modification indices. Now, at the heart of structural equation modeling is that of covariance. And you may recall that covariance is the strength of the association between two variables as well as their variabilities. So essentially, covariance is an unstandardized correlation. It's unstandardized in the sense is that we take into account the standard deviation of the two variables. And it's considered to be the basic statistic of structural equation modeling. This allows us to understand the different patterns of correlations among a set of variables in our model, as well as allows us to explain as much of the variance as possible with the model specified in our structural equation modeling. The logic behind structural equation modeling is that every theory or model implies that there are a set of correlations. These correlations are between what we call latent variables as well as sometimes error terms, and it specifies why variables are correlated with one another. Hence, it's the importance of using theory to draw our models. A necessary but insufficient condition for the validity of the theory is that it should be able to reproduce the correlations that we actually observe in our data. So that we look at what we call the implied covariance matrix, or that what is specified using our model should be equal to or similar to the actual or the observed covariance matrix using our data. Essentially, with structural equation modeling, we are looking for a correspondence between the model that we specify and the data that we've collected. One question you may ask yourself is, why do we use structural equation modeling versus just using either simple or multiple regression? Well, there are three main advantages of using structural equation modeling over regression. The first is that structural equation modeling allows for multiple dependent variables, whereas in regression, we're restricted to only predicting a single dependent variable. Secondly, structural equation modeling allows variables to correlate with one another, whereas in regression, we must adjust for other variables in the model. So we must control for the variables, our other independent variables in our model, to look at the relationship between a particular independent variable and the dependent variable. Perhaps the most important advantage of using structural equation modeling over regression is that structural equation modeling accounts for measurement errors, whereas regression assumes that our measures are perfect. Some of the uses for structural equation modeling are first, and perhaps the most common use for structural equation modeling is to test a particular theory or a model. And we talk about theory testing, we mean examining the strength of the prediction or the associations in the model with the multiple dependent variables, as well as to determine what we call our model fit. So this allows us to look at how good of a model we have compared to a default model where the dependent variables are not related to one another. Structural equation modeling is also used to test for mediation, or what we call our indirect effects. You may think that you can also use regression to look at mediation or to test for mediation, and you are correct. But with structural equation modeling, we don't have to go through a series of steps to test for mediation. Everything can be done simultaneously. A third use of structural equation modeling is to test for group differences, or what is known as multi-sample analysis. So this allows us to look at whether or not our model is a good model for predicting a particular variable in different groups. For example, men versus women, or younger versus older adults. Structural equation modeling can also be used with longitudinal data to test longitudinal models. One thing to keep in mind though with this type of analysis, of course, is that of attrition. With longitudinal data sets, we do know that we have quite a few missing data for individuals at different time points. And finally, structural equation modeling can be used to test for hierarchical or multi-level nested models. Over the next few slides, we're going to discuss the basic concepts related to structural equation modeling. These consist of what we call measured variables or indicators, latent variables or constructs, our measurement model, and our structural model. In terms of our measured variables, or also known as indicators, you may also hear observed variables. These are the variables that we actually measured in a particular study. So for example, if you gave it a questionnaire, these are the particular items on that questionnaire. In this particular slide, we see that our indicators, we have 3 of them. And these are represented in structural equation models as boxes or rectangles. So in this particular slide there, we have those black boxes of hours per week of exercise, intensity of exercise sessions, and money spent on fitness attire. These are the particular items that we ask individuals to respond to on a questionnaire. Meanwhile, our latent variables are what we consider to be intangible constructs that are measured by a variety of indicator variables. So in this particular example, we have exercise motivation being our latent variable or our construct. And to note there is in our structural equation models, we represent latent variables by ellipses. To measure latent variables, it is recommended that we have at least 3 indicator variables. So here in this example, we have 3 indicator variables to represent the construct of exercise motivation. But of course, more indicators are better in our models. What's also to note here is the single-headed arrows that point towards the observed variables. These lines represent the prediction of the observed variables from the latent construct. Now, when we run structural equation modeling, we obtain a beta weight for this relationship between the latent variable and each observed variable. Hence, in this example, there would be 3 regression weights, one for each observed variable and its relationship with the latent variable. Together, the latent variable and the 3 observed variables make up our measurement model. So then we would go on further to test our measurement model, which we'll talk about in a couple of slides. Our structural models, or sometimes called path diagrams, these are used to specify the models in structural equation modeling. And the way that we read structural equation models is that of a causal flow is from left to right. So those variables on the left causing those variables on the right, and from top to bottom. So the variables that are on the top of our models cause those that are on the bottom. In our structural models, we have straight arrows to represent direct effects, so an independent variable predicting a dependent variable, and curved arrows represent bidirectional or correlational relationships between 2 variables. Similar to our measurement model, we have our ellipses to represent our latent variables, and boxes or rectangles to represent observed variables or indicators. Here's an example of a structural model where you see here we have 5 latent variables: aggression, role ambiguity, stress, health, and job satisfaction. Each latent variable is represented by a number of observed variables or indicators. So for example, job satisfaction has 2 indicators, that of supervisor and how much people are paid. Health has 3 indicators, and so on. These ellipses on the ends of each item represent error terms. So each item has an associated error term with it, as we know that our measures are not perfect and they do have some error. So this is again the advantage of using structural equation modeling over regression. Our straight arrows represent our direct effects, so stress, looking at its direct effect on health and job satisfaction. And our bidirectional arrows represent a correlation between role ambiguity, in this case, and aggression. So there's no particular direction of the effect on one on the other. So again, together this forms our structural model or a path diagram. In terms of the types of structural equation models that we can run, there are 3 that we're going to talk about today. That being confirmatory factor analysis, or CFA. And this is important when we look at testing our measurement model. And then for our structural models, we can use 2 different path analyses. So one with a path analysis where we just use observed variables, or those indicators. These could be of particular items or means across a different subscale or scale. And path analysis with latent variables. So this is similar to the example that previous slide showed, where we had latent variables which are represented by observed variables. With confirmatory factor analysis, this is the type of analysis that's used to test our measurement model. This is what we would run first before proceeding with structural models. So you can think of it as a 2-step approach. You must first test your measurement model to make sure that the relationships that are specified between the observed variables and the latent variables are what they should be. And once our model is what we call a good fitting model, then we proceed to the structural model or our path analysis. With confirmatory